Welcome back to the next session. I hope you had a chance to read the or go through the video lecture on the instrumentation or the components used. So now what we will do today is in this video and subsequent to videos, we'll essentially move beyond understanding of just the magnetic, resonance principle and the uh, spin physics and the instrumentation to how is it that we are going to form an image, right? We are interested in imaging. So we would like to see how we are able to convert this knowledge that we have on MR signal. And in fact, not only that, not only MR signal, we also saw how it can be manipulated to get different types of contrast, right? So we talked about polarization of the spins in static field, and then applying RF excitation or the B1 field in XY plane, and then we can detect the signal using a receive coil. And not only that, we also before that talked about different ways to whatever you are receiving, right? How can we make sure that that is sensitive to certain attributes of the tissue property, right? Your T1, T2, proton density, right? So we know all this, but what we do not know is whatever you are recording, right, of this property, whatever you are recording of the signal, where is it coming from? You need to know in imaging, you need to know where the signal is coming from, which location, precisely at high, very precisely at a very high resolution. Only then imaging makes sense. Just to say, okay, I put this patient and this is the signal I'm getting from him may not be meaningful, right? So we should be able to tell the distribution of the voxels of different properties. How do I know what I'm measuring is coming from a particular voxel, right? Particular location. That is the key. So to produce an image, we need to know this spatial location encoding. However, we cannot do that with what we have studied, only with the magnetic field, the static magnetic field, and your receive coil or your transmit excitation. Only with these two, we won't be able to study. But we took a volume and we used static field and excitation field to understand what signal we got. But that is not sufficient. What is sufficient? We need to have some more information, right? We need to be able to locate, encode different locations with something unique. Therefore, we can tell when we get the signal, it came from that particular location, right? It's not a trivial, by no means this is a trivial extension. Imagine, recall that Nobel Prize for the NMR for Bloch equation was given in early 50s, 1952 or something, for the work done in 1940s. Okay, and then Nobel Prize for putting the MRI magnetic resonance image, right? MRI from MR signal were given to Lauterbach and Mansfield only recently. Recently, the relative sense is 2003, less than 2 decades ago, right? It's always viewed in my mind as recently because I was a graduate student working in imaging, and I suddenly, big buzz about a person getting from medical imaging. So that time it was 2003, so it was all very vivid in my mind. So I always tempt to think it is recently, but I know years are passing by. So, but it's still recent enough, right? But more importantly, what is important, what is critical here to observe is from nuclear magnetic resonance, right? Nobel Prize was given in 1952 for the 40s work. These people took, that concept and put it as an imaging system in the 70s, and they got the Nobel Prize in 2003. But essentially, the work was done in the 70s. So, cool 2-3 decades after understanding the physics of nuclear magnetic resonance. So we have just spent about maybe 4 lectures or so finishing the nuclear magnetic resonance physics. We are just jumping here to the imaging solution, thinking as though it's a very straightforward extension or a very intuitive extension, right? So I think you have to appreciate the complex. It's not trivial. I'm going to make it presented so intuitively, try to pretend that, this very common sense way of doing it. But then you have to appreciate you have to really be ingenious to think about all this complex thing, have your own understanding and interpretation. Okay. So what they basically noticed is the precision, Larmor frequency, right? They noticed that that is a very precise measure of the local magnetic. We know this. That's what nuclear magnetic spin was. You apply a magnetic field, all the spins start to align and precess around the magnetic field. Right? This was there. But what they noticed is this is very sensitive. Meaning, if I change the magnetic field slightly, well, Larmor frequency also changes very precisely. Okay, so that is a key observation. Once they unlocked this observation, then they said, oh, I have a whole volume. How do I say that each location is different, right? Or the signal that I am receiving, I should be able to say that it came from different location. They said if this is true, then all I need to do is introduce gradients, right? Introduce changes in magnetic field so that each location is experiencing a unique magnetic field, right? Slightly different magnetic field. If each location is experiencing slightly different magnetic field, that means it is going to experience or it is going to have slightly different Larmor frequency. So the cool idea was by introducing magnetic field gradients, the frequency could be used to identify, because if I have different field strength, then the precision frequency is going to change. And so if I can measure the signal at a particular frequency, I know it came from that location, right? Very, very neat. So essentially magnetic field gradients alter the precision frequency of the spins in a spatially dependent manner. So now we are going to see in a systematic fashion how it was done. Okay. So you can think about it as two broad steps or two different ways of producing an image. Notice we will restrict our attention to only 2D imaging. Clearly, if you just wildly imagine the first principles that we covered, that means I can actually excite all 3D and get the signal. If I can get all different frequencies in the same signal, I can analyze and say this came from that location, that came from that location, because the frequency is uniquely identified. But so we are not interested in volume imaging right now, or the complexities with that. For simple introduction, we will do the 2D imaging. That is, I want to take a slice, so I have a image. Okay, that is what we are going to do. So we can do two things. The idea is I'm going to reduce the 3D problem into a 2D problem, right? So how do I get rid of? I am a 3D volume. So how do I get a 2D image? I have to select a slice, right? We know the normal axial slice, sagittal. So if I can select a slice, then that image is a 2D that we are going to talk. So I have a volume. I have gradients that I can apply in all X, Y, Z. That's what we saw in the instrumentation. So if I want only a particular location, right, to respond, what can I do? Okay, I put it in the magnet. I have everything aligned in the Z direction. Now I can also actually apply gradients, right? So each location has a different magnetic field. But instead what I will do is, I will try to apply the magnetic field, and then what do I need to do? I have to apply my RF excitation. What frequency will I apply RF excitation? I have to apply RF excitation at a particular frequency. Well, particular Larmor frequency which I want to choose. So I can apply my RF excitation during the gradients such that the RF excitation frequency matches only one location, right? So I can select. So selective excitation, meaning I have during excitation. Excitation is the B1 field, the RF excitation that you are doing. So I have a magnetic field gradients to ensure that different spins are there excited. Different spins are there, different Larmor frequencies are there. When I am applying excitation, I will apply a excitation frequency. So I will know only those locations that match to this excitation frequency is going to even respond for the excitation, right? That is the whole idea. Apply B1 at omega naught. That is what we covered. So now I am going to apply B1 at a particular frequency. Wherever that frequency is there in this 3D volume, only that location is going to get excited. What do we mean by get excited? That means it is going to, your signal is going to always in the transverse direction. Excited means only those locations, as long as you apply the RF excitation, only those locations will start to move towards the transverse plane, giving out signal. Okay, so that means if I'm going to measure the signal, record the signal, I know it came from only those locations which had the RF excitation frequency, right? So, but once I get it, it is still going to be volume, right? I'm going to get only a volume because I can apply only, if I apply gradient in one direction, I can apply RF excitation only within a certain frequency, right? So that is going to ensure that I'm going to have 3D collapse to 2D. So when it falls on the floor, I still have everything from that volume, right? Or for that imaging plane. Now what I need to do is somehow tease out within the imaging plane the two other dimensions. Okay, so that we use frequency and phase encoding. So we'll go into this little detail. Right? First, let's start with the slice selection. Okay. So before that, this is the laboratory coordinates that we are going to use for the rest of the material. Like I said, even though I in the physics place we covered always Z as this way and transverse was floor. I told you when showed the MRI photo that the Z-axis is going to be along the patient lying axis. Specifically here, actually, if you notice the textbook, he puts the feet, right, head to feet as the positive Z, and therefore using right hand, right hand thumb rule, right? So this is what he's doing. This is my Z-axis. This is my X-axis. This is my Y-axis. That's how the textbook does it. Okay. So now what I will do is first we'll start about first type of selection, right? So the idea is very simple. I can apply my gradient. I will call Gx, Gy, Gz, so that my net magnetic field is going to be, or the static magnetic field, right, is going to be B naught plus this R. R is a vector which is encoding a X, Y, Z. Here, almost you will see always our direction of magnetic field is predominantly going to be only along the Z direction. Okay. And so we know from before magnetic field strength is related to Larmor frequency. Since the magnetic field strength is a function of R, the Larmor frequency is also a function of R. That is, it is spatially varying in this manner. So this is what we are going to exploit. Okay, now it is 3D. R is X, Y, Z. How are we going to reduce this 3D problem into an imaging problem? First is reduce one variable, meaning select your imaging plane. After you select the imaging plane, within the imaging plane, how is it distributed? Right? That is what we are going to see. So first your selection. We talk about slice selection. So when you do imaging, you always select a slice first, right? When you show an image, you say this is a slice of axial slice, sagittal slice. So image you have is a slice, right? So it's a slice selection. We use what is called as Z gradient. What do we mean by use Z gradient? That is, my gradients, I will only apply GZ. So if I apply GZ, right, I have my Larmor frequency will change only in the Z direction. Or vividly, if this is head, this is tail or foot, you have one magnetic field at the head. Because of the gradient, right, GZ, the magnetic field changes from head plane, right, different planes, axial planes. In the example that we have seen, in the jargon, that notations that we are using, when we change the Z gradient, I am changing the axial slice location, right? I am seeing the axial slice head is experiencing axial plane here is experiencing one magnetic field strength and therefore one frequency. Here is different, here is different. Each plane is experiencing different magnetic field strength. Within that plane, right, in the X and Y direction, everything is experiencing the same in that plane. In plane is same, But out of plane, the magnetic field strength is different, and therefore your Larmor frequency is different. So now you understand that so now you understand, if I have different frequencies, right, because I have different field strengths, when I'm applying RF excitation at a particular frequency, right, that particular frequency, wherever it is matching, only that slice, that location will start to respond. Right, RF excitation, I'm applying a particular frequency, right, wherever that particular frequency is along whichever plane corresponds to that particular RF excitation, only that plane, the Larmor frequency will start to get excited. Rest of the places, it won't be excited. Right? That is the beauty. So now in one stroke, when I apply RF excitation at a particular frequency, I can select a particular plane. Right? Beautiful. So let's think through this little bit. So what are the parameters that I have? Of course, ideally speaking, I have only one perfect frequency, only one single frequency I have to excite. But if I'm going to excite it with a small range, right, V1, V2, or frequency 1, frequency 2, there is a small bandwidth. It is not a perfect sinusoid at one particular frequency. We are going to have a small bandwidth. Then what happens? If there is a small bandwidth, that means you are talking about small bandwidth in B, or spread in magnetic field strength. So the locations are going to be non-infinitesimally thin, meaning it is going to have a thickness, right? So you're going to have a slice thickness in the spatial domain, but in the RF excitation, we will talk in terms of frequency bandwidth, right? So you can see, I mean, here I have two examples or two different field strength. So I said field strength is applied only in Z direction. So here I have a field strength magnitude is GA. Here the field the gradient is steep or shallow, right? You can have different gradients, but it is all only gradient in Z direction. You see the effect already. So if I have the same RF excitation frequency that I apply, depending on the gradient, I actually have two effects that I see. One is the thickness is changing. The other is even the location is changing. In fact, to be honest, you look at this, V1 and V2 is same. That is, I am applying the same RF excitation, but then depending on your gradient, you can have a thicker slice or a thin slice. Not only that, here it is in the neck region, here it has already come to the chest region. So essentially, by controlling the gradient, right, the GZ amplitude of the gradient and the magnitude of the gradient and your frequency of excitation, you can select whichever slice you want from whichever location you want, and the thickness can be controlled, right? So let's put it in terms of equations that we know. So the parameters that we are interested now are RF parameters, which has a center frequency and a bandwidth, and then the slice parameters, which has the slice location and slice thickness. What you need to notice is we are interested in imaging business. So they are going to say the image is from, at this particular location of the brain. So we are interested in slice position and thickness of the slice. So the engineers or the control, the console is going to give parameters that is going to choose the frequency such that the physician or the radiologist can do a study at a particular location. This usually will be a user input or the radiologist input. So frequencies will be changed so that this position is chosen, because everything else is in your control. G is instrumentation parameter, V1, V2 are all your parameter. Gamma is the material property, but here biomedical we said it's all about hydrogen, so we can always calibrate everything else, correct? So now just because I showed you Z as the slice, which is the axial slice. In fact, the beauty about MRI is this: if I applied only, instead of GC, if I applied only GX or GY, I could have selected sagittal or coronal. Not only that, if I apply, all of them together in different proportions, I could even get oblique slides, right? So this is the starting point of the beauty of this modality. You have so much freedom to do what you want. For simplicity, we will keep it, in the X, Y, Z that we have the orthogonal. In fact, even that we will first talk about Z as the axial slice, and we'll continue. But you see the powerfulness of what we have covered so far. Understand the concept, you could do whatever you want. Okay. So just to put it in summarize and move forward. So we have the spatial domain where we are interested in selecting a slice, location of the slice, thickness of the slice. This can be controlled by the gradient and the frequency. The frequency of the RF excitation, the bandwidth of that, along with the GZ controls the location and the thickness of the slice. Okay. So now, okay, we have seen that we have to apply RF excitation within a chosen bandwidth. What is ideal RF excitation? That means it is a hard limiting. That is, I have, the frequency response, right, is a rect, meaning I have all the frequencies only between V1 and V2. Just after I cross V1 or V2 on either side, I don't have any signal, right? That is your ideal rect signal. So excite frequencies only in this range V1 and V2. If you do that, that means your Fourier signal is a rectangular in frequency domain, right? It's a rect in frequency domain. It has only frequencies from V1 and V2. Anywhere else, it is zero. This is your frequency signal. So if this is a frequency response, your time domain that you're going to apply is going to be, rect is going to be sinc, right? So your signal S of t will be a sinc function, which is existing for a long duration, right? So now another parameter of interest for your RF excitation is how long I apply this RF excitation. That will dictate my tip angle, which is related to the gamma, and your apply excitation pulse characteristic A tau t rectaf, this one. Okay, so let's jump into see what so if this is the ideal signal that we are applying. What is this signal? We are applying this to your RF excitation. That is your B1 magnetic field. B1 has to rotate or do, and that is given by this S of t. This is the input to the B. So the B has to be applied. Excitation has to be excited. So excitation at a particular frequency, we know how to denote, right? It's a sinc function with a particular frequency. Of course, we also talked about relating the tip angle to this envelope of B before, right? So now what happens if you have a slightly different frequency than omega naught, right? When the spin Larmor frequency omega is not exactly same as omega, then we need to replace this BE with e power omega 2. Essentially, you have a signal which has omega naught minus omega t, right? So this is my envelope signal, which is envelope is in a sinc format. This is what I'm applying in the excitation. So what is going to be my Larmor frequency at a particular location Z? I know the relationship between field strength and Larmor frequency. They are related through your gyromagnetic ratio, right? So omega frequency at a particular location Z is gamma times whatever is the magnetic field strength at that location, B naught plus, because we are applying only GC, it is GCZ, right? What we are interested is, this is ideal at particular Z, but we know we are talking about thickness. So this is center of the thickness Z dashed. So omega naught is at the center of the thickness, will be gamma B naught plus GZ at Z center, right? And therefore your alpha Z will be this form. What does this say? Your alpha Z is also rectangular. That's what you want to see at that look. What does alpha Z rectangular means? That means only the spins within this slice thickness are responding to this alpha, right? That is what you are exciting. Exciting means if you apply and keep it on, you are trying to push it to the floor. You are saying alpha is also changing only for z minus delta z by 2 to z plus delta z by 2, or within this hard limited bandwidth. So essentially this is saying if I apply a ideal excitation which has only signal in a particular bandwidth, then excitation alpha is also going to be only from there. That means, to stretch your imagination, that means my signal that I am going to record, because remember alpha, when I push it to the floor, you get the maximum signal. So whatever signal I am going to get is also going to be from this ideal slice thickness. But nothing is ideal, right? Practically what will happen? You're going to have some, you cannot apply for infinity, you're going to have some a truncated sink is what you can apply. You have some finite time, right? So when you truncate it, what is going to happen? Your frequency is not going to be hard limiting. It is going to slope out, right? So your slice thickness will not be a rector. Your slice thickness will be, there will be a slope. That is, you're going to have some blurring. So practically speaking, even though we are selecting a slice thickness, we are saying it is from z dashed minus delta z by 2 to z dashed plus delta z by 2. That is your slice thickness. Reality, you're going to get some signal also from the thickness as it is, outside this thickness, because it is moving. How well you contain this is a trade-off that you usually do, right? Very same concept of your windowing in signal processing. Same thing applied here in the spatial domain. Okay. So let's leave it at this. So we say we understand what this is. But what is more important for us to understand is, okay, by doing this, right, I'm going to measure, do I get signal? I said RF excitation will all excite within this thickness. But do you think you will get signal out of this? Why am I asking that question? Because remember how signal comes when everything is coherent, right? But what I have now is, within this bandwidth, I have different frequencies, right? So you can, before doing any further, if you think about it, within this thickness, I have Z bar, right, center of the slice, minus delta Z by 2 plus delta Z by 2, right, the either ends. I have slightly less magnetic field in one direction, on one end. I have slightly more magnetic field strength on the other end, right, because there is a gradient. So what is going to happen? That means this side, the precision is going to be at certain level. One end it will be lower precision, the other end it will be faster. So here is going to spin slow, slightly, compared to the center, and that one is going to precess slightly faster compared to the center, and therefore there is going to also be some phase shift, right? So what is going to happen? The net effect is from this volume, slice thickness volume, you won't have coherent addition. Each one will cancel each other out, so you won't get coherent signal. So if I have to get coherent signal, what do I need to do? Somehow I have to make everything, spin, come in phase, and then spin at the same time. If I do that, then I will get coherent signal out. So slice dephasing means within the slice there are different phases, and therefore you won't get signal. You have to do refocusing to get the signal. You just put, so different Larmor frequencies across the slice gives rise to low speed and fast on the other side, and therefore there is a phase difference also from minus to plus of your thickness, right? So this is a neat solution. What do I want to do? If I can make everything coherent, that means the slow guy have to become faster, fast guy have to become slow. If we do that, then they will all meet. We talked about similar things when we tried to do the spin echo. Just go back and remember. Same logic. Here what we will do is, we will apply gradient, the same Jz, but a negative, right? Initially we did positive Gc. What happens if I do negative Gc? Oh, the field strength that was high, that location will become low. the location that had higher, lower field strength, magnetic field strength, will become high. That means the precision, it was doing faster. Now I've flipped to the gradient, and therefore it is trying to become slow. Wherever it was slow, now because of the flip, it is going to try to come fast. So you can notice that the moment I switch the gradient, the one extreme and the other extreme are all trying to cross path and go to the other direction. The slow side should come to the other, fast side should go to the other direction. So when they cross this path, so after you apply negative polarity, immediately thereafter this signal will start to become increasing because it is getting going. Sometime it is going to give maximum and then it is going to die down. Right? So put it in pulse sequence diagram that we have seen. I apply transmit. While I am applying the excitation, I am applying my Z gradient. So I know this is called my slice selection. Only that slice is going to respond to this excitation. That means I am expected to get signal only from a chosen slice. But you don't have any signal because of lack of coherence, dephasing. So immediately thereafter, when I switch the excitation pulse, after I switch off the excitation pulse, just immediately thereafter, I do gradient switching. The positive GC became negative GC and I apply it half the duration, right? Because it is positive phase on the other direction, the phase difference by 2 is what you have. So you want to make that come together. So tau p by 2. So the moment I apply this, the signal starts to go up. So now the signal, I mean, naturally it will start to decay again, the free induction decay, because the excitation is off, right? So it will start to decay, and I'm going to record my signal as a free induction decay. So this is your analog to digital converter. Essentially, you are saying you are recording the signal and digitizing it. This is your recorded signal. Okay, so we'll proceed with we have a volume. Now we know how to record a volume and how to interpret in using how to explain this using a pulse sequence diagram. So now what we need to do is, you can already start to intuitively imagine, I have a volume, I know the signal is coming. Now from the obtained signal, how do I say it came from a particular x comma y? Right? Z is gone. So within xy plane, whatever I am measuring, how do I say it came from a particular x comma y? That we need to see. Okay, that we will see in the next lecture.